This is a revision video for the GCSE Physics topic of stopping distances, which comes up in Unit 5 of AQA GCSE Physics and Combined Science. By the end of this video, you should be able to define stopping distance and give examples of factors that increase thinking distance and increase braking distance. It goes without saying that moving objects need some time and some space in order to stop. If you've spent much time on motorways in the UK, you'll know that several of them have these white chevrons spaced 40 metres apart, and drivers are told that they need to keep 2 full gaps between them and the car in front. So since these chevrons are spaced 40 metres apart, that means you should be 80 metres behind the car in front. This gap is to do with something called stopping distance, the amount of distance that you travel before you stop. Obviously, it's not great if the car in front of you stops and you're too close behind them to be able to stop before you catch up. We can define stopping distance as being the sum total of something called the thinking distance and something called the braking distance. Now, before we go any further, I want to point out that all three of these terms have distance in them. I have read so many answers from students over the years where they try to describe any one of these terms in terms of the time taken. So it's really important, first and foremost, that when you define any of these terms, you're talking about the distance taken to. Sounds obvious, but needs saying. So the thinking distance is the distance that a vehicle travels during the driver's reaction time. It's important that you're talking about reaction time and not the driver thinking. We're not saying the driver sees an obstacle in the road up ahead and he spends a second or two wondering whether it would be a good idea to brake or not. We're talking about the amount of time it takes from when the driver sort of decides in his head to press the pedal to that signal actually getting to his foot and him actually being able to brake. Then, the braking distance is the distance that the car continues to travel while the driver is braking. It's not the case that as soon as you press the brakes, the car's going to stop. You're going to carry on moving for a little while, and so you are going to carry on travelling a distance. Here are some typical thinking and braking distances for cars moving at different speeds. As you can see, at 30 miles per hour, the total stopping distance for the car is going to be about 23 metres, whereas at 70 miles per hour, our speed limit on motorways, the total stopping distance is going to be more like 96 metres. Time for a quick progress check. How would you fill in the blanks in this sentence? The stopping distance is found by adding the distance the car travels during the driver's reaction blank and the distance the car travels under the braking blank. Pause the video and write down the answers. Our first gap should be the driver's reaction time and the second one should be the braking force. When we talk about reaction times, we mean the time taken for a signal to travel from the brain to reach the muscles, and it does vary by person to person. The normal range is between 0.2 and 0.9 seconds, and you may have tested this yourself as part of the biology required practical. It can be affected and made longer by tiredness, the use of drugs or alcohol, or distractions like using your mobile phone while driving. As part of Biology Required Practical 7, which comes up in the homeostasis unit, you may have already learned how to test somebody's reaction time by performing the ruler drop test. In this test, one person drops a ruler from between the forefinger and thumb of a second person, who has to try and catch it as quickly as possible. We can then measure the distance that the ruler has fallen and use a table to relate this to their reaction time. If you need a refresher or if you haven't done the required practical yet, then click the link above to watch the video. Alternatively, we can test people's reaction time using a computer program. Each time an object appears on screen, the test subjects must press a button as fast as they can. This allows higher resolution data because the computer can measure reaction times to thousandths of a second. The data is also more likely to be valid because there's no way that the computer can accidentally give away that it's about to make an object appear, whereas you might be able to tell from someone's body language that they're going to drop the ruler. However, in order to use this method, you need a computer and a program, and this might not be feasible because you might not have access to a computer, so that might make the ruler drop a better test for you to do. Your thinking distance will be increased by anything which increases your reaction time. Tiredness, the use of drugs or alcohol, or distractions like using a mobile phone. but the distance will also be increased by the speed you're travelling at. Even though your personal reaction time will be the same, whatever the speed is, the faster your vehicle is moving, the more distance it will travel before the signal reaches your muscles to brake. Time for another quick check. Pause the video and write down some answers. Thinking distance is the distance the car travels during the driver's reaction time. It would not be affected by the car's brakes being worn. If the car were being driven slower, then even though the reaction time is the same, the car will have travelled less distance, so that would affect it. And if the driver had drunk 2 glasses of beer, then that would increase the reaction time and therefore would increase the thinking distance. Here are 2 velocity time graphs representing the journeys taken by 2 drivers, one of whom did not get enough sleep last night. Pause the video and write down which graph belongs to the driver who didn't sleep and how you know. So the driver who didn't sleep is the graph on the right, and we can identify this from a couple of things. One, he has a longer reaction time. So here you can see that it's taken nearly 1.5 seconds for him to react, whereas the driver on the left reacted in probably 3/4 seconds. Secondly, we can say that he has a greater thinking distance. If we worked out the area under these 2 graphs, under the horizontal part, which represents his reaction time, we would see that the area under the horizontal part of the graph on the right is greater. And finally, we could also say that he has a greater stopping distance. So again, if we worked out the area under the whole graph, we would also find that it is greater for the graph on the right. Here we have that graphic you saw earlier, showing thinking distances and braking distances. Now, if you just look at the thinking distances, the purple arrows for a second, and you look at 30 miles an hour and 60 miles an hour, you'll see that 60 is double 30 and 18 is double 9. So as the speed that the vehicle is travelling doubles, so does the thinking distance. We can describe this as a directly proportional relationship. So as the speed doubles, the thinking distance doubles. As the speed triples, the thinking distance triples. And we can show this on a graph because it has a straight line relationship and because it passes through the origin, 0, 0. If we now look at the braking distances instead, we can see that this is not a directly proportional relationship. The braking distance for 30 miles an hour of 14 metres is about 1/4 of the braking distance for 60 miles an hour of 55 metres. So one thing that we can say is that an increase in speed has a much bigger effect on braking distance than thinking distance. We can also explain why this is by looking at kinetic energy. The 10th equation from the physics equation sheet that you need to memorise is for kinetic energy, so the amount of energy that moving objects have. We know that we can calculate kinetic energy by doing half multiplied by the mass of an object multiplied by its velocity squared. So let's say I had a car that had a mass of 1,000 kilograms and it was moving at 10 meters per second. It has half times 1,000 times 10 squared joules of kinetic energy, which is 50,000 joules. If that same car then moved at a velocity that was doubled, so 20 meters per second, then it would have 200,000 joules of kinetic energy. By doubling the velocity, we've quadrupled the amount of energy that that object has. So objects that are moving at a faster velocity have more kinetic energy. That means that in order to slow them down, more energy has to be transferred, which we can also describe as more work being done. So here's our second equation from the equation sheet. Work equals force multiplied by distance. When a force is applied to the brakes, work is done by the friction force between the brakes and the wheel. Make sure you're happy that it's between the brakes and the wheel, not between the wheel and the road. We can use all of this information to explain why an increase in speed affects braking distance the way that it does. In this question, Katie is driving when she sees a moose and has to perform an emergency stop, and we're asked to explain what will happen if her speed doubles. Firstly, we should say that doubling the speed will increase the kinetic energy of the car. That on its own is probably worth a mark. If we can then use equations to explain this quantitatively, that's worth a second mark. So EK is half mv squared, therefore doubling her speed will quadruple the amount of kinetic energy that the car has. In order to dissipate that energy, work has to be done by the brakes to stop the car. And so if there's more kinetic energy, more work needs to be done. Work done is force multiplied by distance, and they've told us in the question that the braking force is constant. Her brakes haven't got better just because she's travelling faster. Therefore, if the work done increases by a factor of 4, the distance travelled will also increase by a factor of 4. You should also be aware that in order to reduce the kinetic energy, work is done by the friction force. As you know, friction will lead to a rise in temperature, so the temperature of the brakes increases. If the braking force is too large, the brakes may overheat and that could cause the car to skid. We've already said that the braking distance will be larger when a vehicle is moving faster because the faster car has more kinetic energy, which requires more work to be done, and provided that the braking force is the same, that will require a longer distance. You should also be able to relate braking distance to wet or icy weather. Don't just say weather conditions. It's not going to take me a longer distance to brake just because it's sunny. You need to specify a type of weather which is going to reduce friction and make it harder to brake, like being wet or being icy. Also, poor tyre condition or poor brake condition or poorly kept road surface could also increase my braking distance. Again, you need to be specific. It's not enough to just talk about the car condition. Pause the video and write down an example of a road surface that would affect the stopping distance, and then describe and explain why it affects stopping distance in this way. The stopping distance could be affected by the road being icy or wet or muddy, or really anything that's going to reduce the amount of friction on that road. Any one of these would increase the stopping distance because it will increase the braking distance. They won't have any impact on the thinking distance. The reason for this would be that the frictional force is reduced. We can also use this same physics to explain why it is that lorries have better brakes than cars, and also why their speeds are capped on a motorway at 60 rather than 70. Because a lorry has a much larger mass, when it's moving it will have more kinetic energy than a car moving at the same speed. Therefore, to stop it in the same distance would require a greater braking force in order to dissipate that kinetic energy by work being done. This can be done by the lorry having better brakes, which are able to exert a bigger force. But also, there's a limit to how well the brakes can work. And so in order to sort of remove the need for such a big braking force, by forcing them to travel at a slightly slower velocity, we reduce the size of the force required. To finish, we're going to look at 2 examples that require you to use this type of information. So firstly, a lorry weighing 4,000 kilograms has a velocity of 20 meters per second. Calculate its kinetic energy, calculate the work done to stop it completely, calculate how far it takes to stop, and explain why applying the brakes of the car causes the temperature of those brakes to increase. Pause the video and write down some answers. To calculate the energy, we use the formula half mv squared. So half multiplied by 4,000 kilograms multiplied by 20 squared gives us a total kinetic energy of 800,000 joules. In order to stop the lorry completely, all of that energy must be dissipated, and therefore the same amount of work must be done. 800,000 joules again. If the braking force used was 8,000 newtons, we know that work done is force multiplied by distance. So therefore, 800,000 is that force of 8,000 multiplied by the distance. We can rearrange this to say that the distance is 800,000 divided by 8,000, and this gives us a distance of 100 metres. Finally, applying the brakes causes the temperature to increase because there's friction between the brakes and the wheel. This causes a decrease in kinetic energy and an increase in thermal energy. Finally, we have one more similar example before we finish. In this example, we have a car that is speeding on the motorway, going at 36 meters per second, which is about 80 miles an hour. And this time, instead of coming to a complete stop, it's going to slow down to 30 meters per second. So that's below the speed limit and it wouldn't trigger a speed camera to go off. Pause the video and write down some answers now. For part A, we're going to use the same half mv squared equation that we were using before. So half multiplied by 1100 multiplied by 36 squared gives us 712,800 joules of kinetic energy. Now, there are two ways that we could approach this calculating the work done. We could either work out how much energy the car has at the end when it's going at 30 meters per second, or we could just look at the change, so that change in velocity of 6 meters per second. That's the approach that I'm going to take here. So my change in kinetic energy is half multiplied by 1100 multiplied by 6 squared, so 6 being the difference between 36 and 30. And that gives me a change of 19,800 joules, and that is how much work has been done. If the braking force was 2,500, then what is the distance taken? Well, we already said that work done is force multiplied by distance, and we can rearrange that to be distance is work done divided by force, so that gives us a total distance of 7.92 metres. Thank you very much for watching, and I hope that that was a useful introduction to stopping distances, thinking distances and braking distances. If you did find it useful, then don't forget to like and subscribe below for more GCSE Physics videos coming soon.